So chapter 13.2 is going to be relatively short compared to the other chapters we've looked at because it builds off of a lot of the ideas that we explored in the previous chapter in 13.1. So we're going to continue talking about things you can do with these vector valued functions. And just as a quick reminder, we know those are functions that are in the form like this, r of t, so the output is a vector, is equal to, some function of t in the I direction plus some function with t in the j direction, and then a third one of t in the k direction. So you plug in your parameter, you plug in a specific value of t, and the output of this function is a vector. So we talked already about differentiation of these vector functions, where if the function represented the position of a particle in space, taking its derivative at different values of t would give you the velocity of the curve at that point, and then taking the second derivative would give you the acceleration of the particle at that point. Well, we can do the exact same thing. We can also integrate these vector valued functions and go in the reverse direction. And so integration of these vector valued functions, just like differentiation, is done component by component. So in this example up here, if you were going to take the integral of r of t, then you would just do the integral of f, the integral of g, and the integral of h. So I can write that out a little bit more formally, that the integral of r of t, with respect to t, because t is our independent variable, that's equal to the integral of f of t dt, all of that in the I direction, plus the exact same thing, the integral of g of t dt, plus the integral of h of t dt. And then if you remember, anytime we're doing an indefinite integral, you always have to add on a constant. So plus c. So that would be the full integral of r of t. And so one thing that is a little different with these vector valued functions is because you're not integrating scalar functions, you're integrating vector functions, the constant of integration that you add onto the end is a little bit different. So instead of the constant of integration being a scalar, it is now a vector. So the constant of integration is also a vector. So c is really equal to c, we could do like sub I in the I direction, plus c j in the j direction, and c k in the k direction. Now, if your vector function that you're integrating only has two components, an I and a j, then your constant of integration would similarly only have two components. You would only have two components of your constant vector. So that's kind of all the introduction we need. It's all the integration rules still apply just like they did for integrating scalar functions. But one of the best applications of integration of these vector functions is those initial value problems. And I know those are really common in single variable calculus, and they're really useful for these vector valued functions as well, especially for modeling particle motion through a three-dimensional space. So let's take a look at, we just have one example today, but this one example will really capture all the techniques and the ideas for integrating these vector functions. So suppose we have a paper plane that is flying through the air. We want to know, okay, so suppose we do not know the path of a paper plane that is flying through the air. What we do know, though, is that its acceleration, so the acceleration is negative 32 in the k direction, so negative 32 in the z direction. Its initial velocity, right, so this is part of our initial conditions. So the initial velocity is 8i, 8j, and its initial position is 100k. So its initial position. So we're trying to find the plane's position function. So it gave us the acceleration function, right? The acceleration function is just negative 32 in the k direction. We know the initial velocity, so at time equals 0. So the velocity function at time equals 0 is 8i plus 8j. And the initial position, right, the position function, has an initial condition at time equals 0, and that is equal to 100 in the k direction. So we can kind of construct a little picture of what's going on if I set up some axes. And this will be x, y, and z. So for a little paper airplane, it's starting at a position of 100k, so 100 units up the z-axis. So we'll just label that like 100. So our paper airplane is starting right there, and its initial velocity at time equals 0 is 8i plus 8j. So what does that look like? Let me pick yellow. So 8i, 8j is 8 in the x direction, 8 in the y direction. So the initial velocity vector would look something like that. So that's the velocity vector at time equals 0. And so that will kind of look like that, where those are 8 and 8. And then we know that the paper airplane experiences a constant acceleration downwards with magnitude 32. So across its entire flight, there's a constant acceleration downwards, a downwards force of 32, acting on the plane throughout its entire flight. So let's start working backwards to find what that flight path looks like, or the position function. So the first thing we're going to do is we'll just integrate the acceleration function to find the general velocity function. So here's all our setup. So the first thing we'll do is integrate the acceleration to find the velocity. So v of t is equal to the integral of acceleration. And so what is that going to be? That is the integral of negative 32k in the k direction dt. So all that is going to be is negative 32t in the k direction plus a constant. And I'll call that C1. Now we just got to find out what C1 is. So if we know that v of t is equal to negative 32tk plus a constant, now we'll use our initial velocity condition to find out what that constant needs to be. So in this case, plugging in 0 needs to equal 8i plus 8j. So we'll plug in 0 to match our initial condition. That's going to be 0 plus C1, which has to equal 8i plus 8j. So from this, we know that C, the constant, has to just be 8i plus 8j. C1 has to be 8i plus 8j. So we used our velocity initial condition. So now we know the full-fledged velocity function is 8I plus 8j minus 32tk. Cool. So now that we have the full velocity function, let's integrate one more time, do the same process again to get down to the position function. So now we'll integrate, we'll know r of t, the position function, is equal to the derivative of velocity. So that's going to be the integral of 8I plus 8j minus 32 tk dt. And so we'll just integrate component by component. So we'll get 8ti plus 8tj minus is going to be minus 16 t squared k, yeah. Minus 16 t squared k plus another constant. I'll call that C2. So now we have to find out what the second constant is going to be. So so we know that the position at 0, so r of 0, has to be 100k. And so that will have to be r of 0. So let's plug in 0 here and see what we get. So when you plug in 0 here, you end up getting just 0, right? You get 0, 0, 0. So that ends up being 0 plus C2, because all of those terms have a t in it. So then we know that in this case, C2 must be just 100k. So let's put that back into our position function. So we know the full version of the position function is 8ti plus 8tk plus, where we have the minus 16 squared t, minus 16t squared. And then, because the constant only has a k component, we're only adding it to the k function, so plus 100, all of that in the k direction. So that is the final flight path for a paper airplane. Just one note is, if either of these constants had, or if this one in particular had more components, like say it had 6i plus 100k, then the 6i component would be added on here. So you would get 8t plus 6 in the I direction, and then you would add the k part, the 100, to the k component. So you just add in the parts of C that correspond to the different components. That is also done component by component.